after defining the definition of, or after defining, we can say differential equation means what, what are types of differential equation, how do we define the order, degree, then linearity and homogeneity. Okay, we'll move towards the few numericals of differential equation. Okay, so out of which the first is, suppose given like that, d square y by dx square plus under root dy by dx plus y is equal to 0. My question is, find out the order and degree of this differential equation. Okay, so first job is to simplify this. So how will I do that? D square y by dx square plus y, okay, is equal to minus under root dy by dx. Okay, now simply square it. So we can say squaring both the sides. Okay, what we will get over here? D square y by dx square plus y bracket square is equal to dy by dx, because this under root will go and we'll get dy by dx. So if you simplify this, what will I get? This is a plus b bracket square will give me d square y by dx square plus 2y d square y by dx square plus y square is equal to dy by dx. Okay, so if we arrange this equation properly, which is d square y by dx square plus 2y d square y by dx square minus dy by dx, this term will go to LHS, plus y square is equal to 0. So this equation is properly simplified, and now we are in the position to get our degree and order of this differential equation. Okay, so as far as the degree is concerned, first I taught you order. So we'll talk about the order. So we can say over here order is 2 and even degree is 2. Correct? Order is also 2 and degree is also 2. Okay, one thing I purposely did not write, which is this has to be squared. Correct? This is d square y by dx square bracket square plus 2y d square y by dx square plus y square. So that's the reason order is 2 and degree is 2. So like here I mentioned, how much is the order? Here also we need to write this order. Okay, so order is the highest derivative it contains. In this case, the highest derivative is this. Okay, as far as degree is concerned, this is my degree and this is my order. Okay, so that's why we have understood, or we have finished, or we completed one problem as far as get the value of both order and degree. Correct? Now we'll move towards the next problem. Next problem is d cube y by dx cube, correct, plus x dy by dx raised to 3 by 2 plus x square y is equal to 0. Okay, now this equation we need to simplify it further. So how will I write this equation? This is x dy by dx raised to 3 by 2 is equal to minus d cube y by dx cube plus x square y, put it in a bracket. Okay, now again as usual squaring both the sides. So if at all I square it, what will I get? X will be x square and dy by dx will be square, and this is 3 by 2 will get cancelled, is equal to d cube y by dx cube square plus twice x square y into d cube y by dx cube plus x raised to 4 y square. X square ka square will be x raised to 4 y square. Okay, so how much is left now? We will arrange the term properly and we will get the final solution as far as degree and order is concerned. Okay, so we'll write this term first. So this is d cube y by dx cube bracket square, done, plus twice x square y d cube y by dx cube, this term, okay, we wrote first, then minus x square, okay, this term has come over here, we can say minus x square, because maximum terms are on this side, better to take this term over here and simplify it, okay. So minus x square dy by dx cube plus x raised to 4 y square is equal to 0. So now the term is arranged properly, okay. So in this case, what we can say, the order and degree, okay. So we can say the order is 3, okay, and the degree is 2. Degree is 2 and order is 3, okay. So order is 3 and degree is 2. This is the way we will be solving the numericals over here. Next question is d square y by dx square plus 2 dy by dx plus x is equal to 0. This is differential equation given to you. You need to check the order and degree, okay. As far as this term is already simplified properly, there is nothing much work left in this case. So we are in a position to mention the order and degree easily. As far as order is concerned, we can say d square y, correct. So over here we can say order is 2. As far as degree is concerned, this has got the power 1, so we can say degree is 1, right. Next, this equation dy by dx cube plus d square y by dx square is equal to x. As far as this x is concerned, we can take it on this side and say d2y by dx square plus dy by dx cube minus x is equal to 0, correct. So as far as this is second order, okay, so obviously this is bigger than this. This is just d square y by dx square, this is dy by dx. Even though it's cube, do not have to get confused, okay. So as far as this term is concerned, this is raised to 1, okay. So we can say very confidently that the degree is 1 and order is 2, okay. Order is 2 because this is d square y and the degree is 1, okay. This is the way we will be solving problems over here. Next part, as I mentioned, is concept of singular point. So to understand this singular point, I have considered one second order linear homogeneous ordinary differential equation. As this side is 0, okay, so it's a linear equation, okay, it's a homogeneous equation also. As it's arranged properly, d2y then dy by dx plus y equal to, correct. So this is my second order, okay, linear homogeneous ordinary differential equation. Now to check the singularity of the above equation at x is equal to x0, what we need to do? The first point is, if px and qx, okay, both remains finite. So first is px and qx remain finite at x tends to x0, then the point x is equal to x0 is the ordinary point of the given differential equation, correct. And second point is what? If either p of x or q of x or both diverge, okay, means tends to infinity, as x tends to x0, then the point x is equal to x0 is said to be singular point, correct, singular point of the given differential equation. So first we said ordinary point and second we said singular point, okay. Now as far as singular point is concerned, there are two types of singularity. One is regular, okay. In regular, what we understand over here, one is regular or non-essential and second will be obviously irregular. So first we'll talk about regular or non-essential singularity. singularity. So in this case, what we do, if either p of x or q of x or both diverge, okay, at x is equal to x0, but x minus x0 p of x and x minus x0 square q of x remains finite as x tends to x0, then x is equal to x0 is said to be a regular singular point of the given differential equation. The second point, what I said, is the irregular singular point. So how do we define that? If x is equal to x0, this is the point of our interest, is a singular point such that p of x diverges faster than 1 upon x minus x0, that is x minus x0 into px tends to plus or minus infinity, okay, as x tends to x0, or x minus x0 square qx tends to plus or minus infinity as x tends to x0, then this given point x is equal to x0 is said to be irregular singular point of the given differential equation. Now, to understand this, we will solve few problems, okay, which will help us understand better that the given equation has got an ordinary point, singular point, regular singular point, or irregular singular point. Here we said ordinary point, second one was singular point, but in singular, is it regular singular or irregular singular? That we will understand with at least 4 to 5 problems. So out of which first problem is, not the first problem. What is the first problem? Show that x is equal to 0 is an ordinary point of the given differential equation. What is the equation? D square by dx square minus 2xy dash plus 2 lambda y is equal to 0. I'll arrange this equation properly. So d square y by dx square minus 2x dy by dx plus 2 lambda y is equal to 0. This is the given differential equation. Now I need to arrange it in this fashion. Okay. So what is this part? This is my px. Okay. And what is this? This is my q of x. Q of x y. Y is over here. This is p of x dy by dx. Okay. P of x dy by dx. So what I understood, px and qx are known. Okay. I want to check x is equal to 0. Okay. So what will I do? I'll say p of x is minus 2x and q of x is 2 lambda. Okay. Now what is the point you need to check? At x is equal to 0. Fine. So what we'll say? Limit x tends to 0 of p of x is equal to limit x tends to 0 of minus 2x will be 0, because x tends to 0. Okay, this is 0. So this is 0. So we can say finite. Okay. Similarly, limit x tends to 0 of qx will be x tends to 0 of 2 lambda. Okay. This will be again finite, because there is no x term over here. So this is 2 lambda only. Correct? This is finite. So as this p of x and q of x are finite at x tends to 0, hence the given point x is equal to 0 is an ordinary point of the given differential equation. So here we can say this is x is equal to 0 is the ordinary point, because what is the definition? First we said either ordinary, singular, regular singular and irregular singular. So ordinary means px and qx remains finite at x tends to x0. In this case x0 is 0. So we have found out finite, therefore x is equal to 0 is ordinary point. So it's that simple. Similar problem, show that x is equal to 0 is ordinary point of differential equation. What is the equation given to you? D square y by dx square plus xy dash, that plus x square plus 2y is equal to 0. So first I'll arrange the equation properly. Plus x dy by dx, okay, plus x square plus 2y is equal to 0. So this is my px, this is my q of x, okay. So what is the condition? The point is x is equal to 0. So what is what I said earlier? Limit x tends to 0 of px will be limit x tends to 0 of x, okay, will be 0, which is finite, correct. Then limit x tends to 0 of qx will be limit x tends to 0 of x square plus 2, correct, which is 2, because 0 square will be 0 plus 2, which is finite, correct. So as both these limits turned out to be finite, therefore we can confidently say that yes, x is equal to 0 is an ordinary point of the given differential equation, okay. Now we'll move towards the next question. Next question, question number 3. Show that x is equal to 1 is an ordinary point of the differential equation, which is 2x square d2y by dx square minus x dy by dx plus x minus 5y is equal to 0, okay. So first job is to make this in a standard differential equation, which is this one, okay. So how will I do that? I will just do it by, I don't want this term over here, so divide this term over here and over here. So what will I get? I'll get d2y by dx square minus x divided by 2x square dy by dx plus x minus 5 divided by 2x square y is equal to 0. So now it has come in the proper format, d square y by dx square plus px dy by dx plus qxy is equal to 0. So my px is this and qx is this, correct. So now I need to check at x is equal to 1 point. So we can say limit x tends to 1 of px will be limit x tends to 1 of minus, because usually I have in equation I have a plus sign, correct. So px has got a minus sign over here. So we can say minus x divided by 2x square, correct. So this is 1 by 1 square, correct. So answer will be minus 1 by 2, which is finite, okay. Similarly, limit x tends to 1 q of x is equal to limit x tends to 1 of x minus 5 upon 2x square, correct. So this will be how much? 1 minus 5 upon 2 into 1 square, which is minus 4 upon 2, which is minus 2, which is finite, correct. So as this px and qx are finite, hence we can say x is equal to 1 is an ordinary point of the given differential equation. So we have solved this pattern. Now we'll go towards the regular singular and irregular singular examples. Next problem, show that x is equal to 0 is a regular singular point of the given differential equation x d square y by dx square plus 1 minus x dy by dx plus lambda y is equal to 0. Here we are saying it's a regular singular, not an ordinary point, okay. So how to check that? So what we can say, what is the px first? I don't want even x over here, so first divide by that x. So we can say arrange the equation properly. So d2y by dx square plus 1 minus x upon x dy by dx plus lambda upon xy is equal to 0. Done. So as far as this equation is concerned, okay, what are the values of px and qx? P of x is 1 minus x upon x, and q of x is lambda by x. Fine, lambda by x. Now what I can say, that when x is equal to 0, okay, what will happen? Q of x is equal to lambda by 0, okay, will be infinity. That's the reason x is equal to 0 is a singular point of the given differential equation. This is not a finite nahi hai. If it is finite, then we would have said ordinary. So this is surely singular point. Now we need to check, is it regular singular or it is irregular singular. That job is left. Correct? So now over here, it's very interesting, no? So to check the singularity, what I taught you, first we have to check xpx. Okay, so what will I do? What will I say? X into px. How much is px? 1 minus x upon x. So I can cancel this and say it is 1 minus x. Done? Okay, so if at all I take the limit now. So limit x tends to 0, xpx is equal to limit x tends to 0, 1 minus x is 1 minus 0 is 1, which is finite. Great. Similarly, what I want for the qx also. What is the for a similarly condition for the qx? Similarly, we can say limit x tends to 0, x square q of x, okay, will be limit x tends to 0, x square q of x is how much? Lambda by x. So it will be how much? 1x gets cancelled. It is x lambda, which is also finite. Done? So if it is finite, then we can very well say xpx and x square qx remains finite as x tends to 0, therefore regular singular point. Okay.